I'm not going to work both of them because, you know, at some point you guys have to be accountable for this, but I am willing to work one of them. So do you want me to do number one or number two? Two. Okay. So number two is the one with two capacitors. Says the jackass with a PhD. All right, so this is, I believe, pretty darn similar to the first problem that I showed you guys, except that instead of having an inductor right here, it has a capacitor right here. But let's take a crack at it. So we've got some voltage source here. VS, I believe, in series with some resistor that I'm going to call R1. We have a switch that is closing at t is equal to 0. Then I have a resistor R2 in series with a capacitor that I'm going to call C1. That path is in parallel with a capacitor over here that I'm going to call C2. I think that pretty much does it. So I'm calling this voltage Vx, which would make this current Ix. This voltage will be Vy. And this current will be Iy. Okay. Numbers are bad, so I'm not going to use it. All right, so I'm going to approach this literally the exact same way I approached the first example problem that I worked for you guys. I'm going to apply Kirchhoff's current law at this top middle node during the transient condition, and then I'm going to write the Kirchhoff's voltage law equation around the right-hand loop. So let's do our KCL equation first. I'm going to write that as the current flowing in, which would be Vs minus Vy divided by R1 will be equal to Ix plus Iy. And now I'm going to express Ix in terms of the capacitor C1 and the voltage Vx, and the capacitor C2 and the voltage Vy. And I'm thinking about changing the names of the capacitors to Cx and Cy so that I don't confuse myself. So I'm probably going to do that real quick here. Just so that all subscript Y are associated with the same thing, all subscript X are associated with the same thing. All right. So I'm just going to go ahead and do that up here, and then I'll get things smaller, as it were, in a moment. So let's see. So the current flowing through a capacitor is C times the derivative of the voltage. So that's going to be Cx dVx by dt plus Cy dVy by dt. And now just for the sake of argument, let's put the derivative of Vx on one side by itself, okay? So the derivative of Vx with respect to time is going to be equal to, so let's see, this part's staying over here where it is. So I'm going to have Vs divided by Cx_R1 minus Vy divided by CX R1 minus CY over CX times the derivative of VY with respect to time. So let's double check the algebra there because I did a lot of things. I don't want to make sure I don't screw anything up too much. I effectively divided both sides through by CX. So I should have a VS over CX R1, which I have right here, minus a VY over CX R1, which I have right here. I'm going to have a CY over CX times the derivative of VY with respect to time, and I'm moving it to the left-hand side of the equal sign, which is why it got the negative sign here. So I believe my algebra checks out to be okay. And I'm going to call this guy equation 1. Now I'm going to do Kirchhoff's voltage law around the right-hand loop. And so that tells me that Vy is equal to R2 times Ix plus Vx. Right? So I'm saying this voltage drop is equal to this voltage drop because they're both in parallel. And the voltage drop over here is the current flowing through the resistor times the resistor plus the voltage drop across the capacitor. Walker, are you raising your hand or just holding it oddly? Raising your hand.
I have a question.
Yeah.
So IYFT on the actual question on the output is above the capacitor. Does that make a difference?
Not at all. No, because if it's the current flowing through the capacitor, it doesn't matter where it is as long as it's flowing through that capacitor. The only real change might be is if the current was direction up, in which case we would just everywhere we see an IY put a negative sign, but I'm not going to do that to be annoying. Yes.
For your first equation, your goal is to just get EVX by itself.
Generally speaking, I'm just trying to get two equations that somehow relate my capacitor voltage for this first capacitor and the capacitor voltage for the second capacitor. I'm just trying to relate trying to think how to put this. The not derivative relationships. So capacitor voltages or inductor currents, because I don't have any inductors here. I don't care about having inductor current or anything like that. So I don't want to have I's anywhere because I'm dealing with capacitors. I want to only have the voltage drops across the capacitors. If there were an inductor, I would want everything expressed in terms of the inductor current. For a capacitor, I want everything expressed in terms of the capacitor voltage. Okay. So we're going to express this Ix in terms of Cx and the derivative of our voltage. So I'm just going to do this over here. So that's going to be R2 times Cx times the derivative of Vx with respect to time plus Vx with respect to time. And that's actually pretty okay. So I'm just going to get rid of this middle bit right here and just say that Vy is R2 Cx times the derivative of Vx with respect to time plus Vx with respect to time, and call this guy equation 2. So now I need to figure out effectively which of these two bad boys I'm going to wind up taking the derivative of to sub into the other. So let's look. I think I'm going to take the derivative of equation 2. So let me explain that really quickly here. My first thought was I was going to take the derivative of equation 1 because that would give me obviously the second derivative of Vx is equal to some other stuff. But I have Vx here, or the derivative of Vx, which I know what that is. Then I would have the second derivative, but nowhere would I actually have Vx isolated by itself. And I think I've made it abundantly clear, I don't like integrals and I never want to do them. So to make my life easier, if I take the derivative of this guy right here, I will get the derivative of Vy with respect to time, which I can plug in here. I already have Vy with respect to time, which I can plug in here. And so this equation will be only in terms of Vx, which is really what I'm looking for. So I'm going to take the derivative of equation 2. So that says the derivative of Vy with respect to time will be R2Cx times the second derivative of Vx with respect to time plus the first derivative of Vx with respect to time. Here's equation 3. And now I can sub 2 and 3 into 1, right? So in equation 1, and that'll be fine. To skip a step here, I'm going to move this Vy over Cxr1 to the left-hand side, move this Cy over Cx times the derivative of Vy over to the left-hand side so that all of my Vx terms will wind up being on the left-hand side. So, let me write this out real quickly here. So dvx by dt plus Vy divided by Cxr1 plus Cy over Cx times the derivative of Vy will be equal to Vs over Cxr1. So that's just rearranging equation 1. Now I'm going to do the substitutions. So Vy is up here, so that's R2 Cx times the derivative of Vx with respect to time plus Vx Vy over Cx times the second derivative. No. Multiplied by our first derivative relationship. Nope. Making a simple mistake here. I'm just plugging this in. I just lost my place. And now I believe if I've done these substitution correctly, I'm just at the point of algebraing things up to get coefficients where they need to be. So starting with my second derivative equation, I have Cy divided by Cx times R2 times Cx. So the Cx's are going to cancel each other out. So I should get R2 Cy times the second derivative of Vx with respect to time. That's this guy taken care of. Now I'm going to have my first derivative terms. So over here on the left-hand side, I have just 1 from this guy. Then I'm going to have R2 over R1. From this guy. Then I'm going to have CY over CX from this guy. And I believe those are all of my first derivative terms. And then I have my just Vx by itself terms, of which there are 1. So plus 1 over CX R1 times Vx is equal to Vs over Cx R1. So let's see if I can do this today without screwing it up. Alpha should be 1 plus R2 over R1 plus CY over CX divided by twice R2 CY. Omega naught should be the square root of 1 over R1, R2, CX, CY. Or this guy right here is just 1 over CXR1 multiplied by 1 over R2C1. Algebra look okay? And then at this point, put numbers in, use the table, same old crap. Yeah, so the coefficient on the second derivative term needs to be 1 in order for alpha to be the coefficient of the first derivative term multiplied by 1/2, and in order for omega naught to just be the square root of the coefficient of the 0th derivative term, or the function by itself. That coefficient, the coefficient of the first derivative term, divided by the coefficient of the second derivative term, because we need this effectively to be 1 times the second derivative plus b times the first derivative plus lowercase c times the 0th derivative. And I'm just doing that in a single step by dividing through by this coefficient. Okay. Oh, and well, it doesn't really matter, but this term is also going to get divided through, but it literally doesn't matter because we don't use it for anything. So why give a shit? Yes.
So do you have any kind of guaranteed way of thinking equations that you come up with, or is it just like big stuff?
So I personally usually wind up writing one KCL equation and one KVL equation and just seeing what shakes out. Like I said, you can definitely use nodal and mesh, but I find that it's not worth the hassle of setting everything up, solving that system with derivatives and second derivatives and all of that kind of stuff by hand, and then going back out to relate it to the quantities that we're interested in. Whereas just using KCL and KVL keeps everything in terms of what we're looking for to begin with. So I find it much, much easier. Realistically speaking, the circuits can't get much more difficult than this because all we can do this for is a second order circuit. Anything third order and higher, the math just gets so terrifyingly gross that Laplace transform is what we'll wind up using in circuits 3. But because you guys haven't all been exposed to that yet, we can't use it and make our lives easier.
That's next one.
All. Yep. Just as a heads up, when we're using the Laplace transform and all of that kind of stuff, we actually don't. We can do the transient analysis and the steady state analysis at literally the exact same time. It's all just one analysis thing, which is actually pretty interesting. Yes.
Can you explain how you got your very first equation again?
Sure. So my very first equations, let me underline things. So this is a current, and it's the current flowing into this node. And then this is a current that's flowing down here. And this is a current that's flowing down here. So it's literally just Kirchhoff's current law at this top node, with the current flowing in is equal to the current flowing in. So I'm saying that the voltage drop across this resistor R1 using Kirchhoff's voltage law around this outside loop is just going to be Vs minus Vy, and then divide by the resistor. So after that, it's just moving crap around to make it look nice. And then I wound up having to move it around further when I realized it didn't look as nice as I wanted it to.
Why wouldn't the current flowing into the top node just be Vs for R1?
That would be assuming that there is no voltage drop across this path or no voltage drop across this path, which how can we make that assumption? For this current to be just Vs over R1, this node needs to be tied to the negative polarity terminal of the voltage source, and it very much is not. There's this path in the way and this path in the way. Excuse me. So if there's an opportunity for a voltage drop to happen because there's something that isn't a short circuit, we have to assume that that voltage drop is going to be something. If we find out that it's zero, that's great, but we can't just say it's zero just for the sake of saying, well, we'll make the math really easy. It'll also probably not be correct.
Written class test is just gonna be like series parallel RLC that they don't.
Yep, exactly right. So to reiterate, I believe I said this on Monday because I totally know what day of the week it is. Your in-class test on Friday will consist of exactly 2 problems. One will be a series RLC circuit. The other one will be a parallel RLC circuit. So one of them will have a dependent source. The other one will not. And the one that doesn't have the dependent source will be a total response problem where you need to find stuff at t is equal to infinity. And just to be clear, the problem on your exam is going to be broken down just like the homework problem. So I'm going to say solve for blah, blah, blah at 0 minus, then 0 plus. If you need to do it at infinity, I tell you to do it at infinity. If you don't need to do it at infinity, it's not on there. Just so that there are the same number of steps for both problems effectively. Because instead of having a step for solving for everything at infinity when it's not needed, you're going to have to determine the equivalent resistance of the system because it's going to have a dependent source kind of thing. Yes.
Are you cool with us plugging in the 2x2 system straight into the calculator, giving A1 and B or A1 and A2?
I want some work because if you make a mistake and you don't have any work, I'm going to give you a terrible grade. just to be real clear, yeah. So if you're crazy confident, then that's on you. But I would write stuff down just in case. It's only two problems.
Write down the equations.
Yeah.
Coefficients. So.
Yeah. I mean, if you've done these enough, you can do 70% of it probably in your head or damn near it, but it's still better to write things down just in case, in my opinion. Don't give me something I can't give you partial credit on just in case you screwed something up. Yes.
How would you rank the list of FD approved calculators, like best to worst?
It depends on what application. So the worst is actually quite easy. Okay, no, the worst is actually very easy. The worst is the TI 30X. That is a peasant calculator. Don't use it. One step up from that is the HP 33S, which is witchcraft. I do not understand how HPs work. Then I would say it is the Casio 115. And then it's a tie for me for the TI 36X and the Casio 991. So I like the Casio 991 because it's capable of solving a 4-equation, 4 unknown system, which it's the only FE approved calculator that can do that. What I don't like about the Casio 991 is that you have to actually switch the calculator mode in order to use to do complex number math, which annoys the hell out of me because I'll start typing out an equation and then I go to press the engineering button and it's just like, this doesn't do anything because I forgot to switch the damn mode. The TI 36X can't do a 4-equation, 4 unknown system, but it can do all of the complex math without changing anything. And also I find that you can store variables and recall variables more easily with the TI than you can with the Casio. So my personal preference is the TI 36X, but the Casio 991 is very close.
Should they discontinue the 991EX?
Did they?
Yeah. And they released this one instead, which is really retarded.
Don't use that word kind of thing. May I see that one?
Yeah.
If it's a 991 anything, it's that. Yeah, completely different layout.
Now it's like price scales and marks on for like 6 months.
I don't like that. But I'm sure I could get used to it. Well, there's 7 to 8 feet. Those things are just- All right, anything else?
What do you expect is gonna be able to take off?
One, just one. Comparable in difficulty to the second example that I worked in class on Monday. I don't remember whether or not I put 2 inductors, 2 capacitors, or a combination of an inductor capacitor, but I think it's got like multiple sources or something like that to make it a little bit more challenging, but it's the same. Yeah. All right, you guys have a great rest of your day. I'm gonna go hide in my office.